Right. Lastly, we started to talk about the forms of energy. Right? Lastly, we started to talk about the forms of energy, right? Energy is simply defined as a capacity to work. Right? I know you all might never open this handout, so that's write it down now. Energy is defined as a capacity to work. Energy is defined as the capacity to do work. Right? It's a capacity to do work, right? And let's just write down what is work one time. Write this down. Work is equal to you. Write that there. Work is equal to force multiplied by the distance moved. Work is equal to force multiplied by distance moved. Right, so work done is equal to force multiplied by the distance moved. Right? What's the SI unit for work? The SI unit for work is joules, right? You'll see it right here. 1 joule is 1 Newton meter. Right, so make a note of that, please. The SI unit for work or energy is joule. The SI unit is joule. Right, 1 joule is 1 Newton a meter, 1 Nm. Right, and we talked about the conservation of energy. The conservation of energy states that energy can neither be created nor destroyed. So energy exists around us. All we can do is just convert the energy from one form to the next. That's okay? So just make a note of that in red. And then let's just go over the different types of energy. You don't have to write all that. Just write the conservation of energy. Right? Energy can neither be created nor destroyed, but can only be converted from one form to the next. Right? So before we focus on two types of energy, let's just run through the whole list, right? I think we talked about them yesterday, right? So these are all the different types of energy. Number one, chemical energy, right? Released during chemical reactions or transformation. You'll find them in food, battery, fossil fuels, and so on, right? Electrical energy is the movement of electrons, power lines, lightning. Kinetic or mechanical occurs during physical collisions and movement, right? So kinetic is movement, right? A rolling ball or a falling object. Where which Then you have gravitational potential, that's the energy possessed by a body by virtue of position, such as height. So an aeroplane in midair has potential energy, a car on a cliff has potential energy. You standing on top of a table has potential energy. All right. Then you have elastic potential. Where did we see elastic potential? In Hooke's law, right? In Hooke's. So all those springs have elastic potential energy. Energy that can be stored within an object during experiencing deformation. Compressed spring, slingshot, catapult. Electromagnetic, held in waves such as X-rays and radio waves, right? Transmitters on TV screen, they produce EM waves, right? Like in microwave, they produce microwaves, which is an electromagnetic wave. Okay. Nuclear, released during the splitting of atoms, right? This is like in a uranium nuclear reactor. Sound energy associated with vibrations of matter, vocal cords, music, tires, preaching, and so on, right? And then thermal. Thermal exists everywhere. If you clap your hands long enough, you will start to feel the thermal energy between your hands, right? So thermal energy is the energy that can be stored or transferred across molecules through kinetic energy. Heat from friction, wasted energy from a plant, and so on, right? So if you were to check your pan, right, your pan normally be hot, right? Because it's converting the electrical into other forms as well. So what we need to look at now is something called the conversions of energy, right? So note that energy transfers in the following. A car being driven on a straight road, right? What would be the energy being converted in a car moving in a straight road? What's the supply of energy in a car? Gas, which is chemical energy, and that chemical energy is providing what form of energy? Mechanical, making it turn, right? And after mechanical, you will get sound and always heat. Heat, right? Thermal. All right. So we have to be able for each one of these to explain the change in energy, right? Hold on now. So burning match. What's the energy conversion there? Burning match. Heat. Well, that's the product. The product is thermal, right? What's the source of energy? Chemical, yeah, you go chemical, graphite, right? I mean that's the graphite. No, on the mastic is sulfur, right? Right? So yes, so chemical to thermal. Anything else? A mastic. Soda, but something else. Something else in a lighted match. Chemical to heat plus something else. In the dark. Light energy. Okay, light as well. Oh wait, sorry, the other right come. So head of energy conversion, and write the conversion down for 1 and 2. Good. The first two, right? Do the first two. Then let's try the third one. Object falling from the shelf. Do the third one, and then I'll pick on somebody. Right? I want the conversions of energy in slingshot. Right, let's see what you got. Slingshot. Can I hear yours, Amelia? I don't like gravitational. What about elastic potential? Right? So we can start with the slingshot. We can start with elastic potential energy. What is that converted into? Kinetic energy. Right? And since we're now practicing, you have to write thermal as well. Thermal always being produced. Right? Thermal is always being produced. You might necessarily feel it, but the rubber gets hot. Huh? And sound wave. But take sound as well. Number 4. Object falling from a shelf. What you would say? Gravitational potential to. You miss something. And you miss something. Kinetic it moving, right? So it goes from gravitational potential energy. That potential energy is converted into kinetic, sound, and of course thermal. Okay? All right. So that's others to look up, right? But most important, since we're on kinetic and potential, let's focus on those two. All right? So head up kinetic and potential, head up kinetic and potential. So we are going to focus on those two types of energy. The others try them for homework. Right. Here we have the two main types of energies that we are going to focus on. Kinetic energy and gravitational potential energy. As we said, kinetic energy has to do with what? Motion, right? So what do you expect to see in the formula? Something with motion. If you look at your formula, the formula you will see velocity in it, right? Because kinetic energy deals with motion. All right? Gravitational potential deals with height, right? So in its formula, you will see height. You okay with that? Right? Write those two now, please. Kinetic and potential. Write the formula because we're going to be using that a lot. Triangle means change. Triangle means change. No, this is the actual meaning. Finish. Finish. Right. So we want to take a look at how kinetic and potential being converted, right? Let's take a look at this simulation in. Oh, I just stop that. What do I do? I'll take it over. Right, what you see? Here we have an example of pendulum, right? Here we have a pendulum. On the pendulum, like by the way, a pendulum is a string without a curve, right? What we're going to observe, we're going to observe the change in kinetic and potential energy as the pendulum moves, right? Where is the graph? There's the graph there. Let's just place it. Which one going up there? PE. Potential, right? You're seeing that? So the further I go from the middle, the potential increasing. You're seeing that? When I release it, which one going up there? Which one? As it moving. So check it right here. Which one's the largest here? Let's see if I can pause it. Okay, horrible. Right? Right. So which one's the largest all the way out there? Potential, right? The blue, see the light blue? The light blue is the largest. Let's see if we could. Can I get it? Going to slow. Right, see it better now? Look in the middle. See when it hits the middle, kinetic is the most, and then when it reaches the highest, potential is the greatest. But what is happening in between the journey? What is happening in between the journey? Why was it, Mariah? What happening to between kinetic and potential during the journey? Right. When one goes up, the next goes down, right? So what that means is that, remember we learned energy is always converted from one form to the next. We learned that. Right. So if you look here, look at the potential, full of potential here. And that potential converts to kinetic. Now, that kinetic converting back to potential, come back down, convert back to kinetic, going back to potential. So there's always a conversion of kinetic to potential. You're seeing that? Is there a point in time in the journey when both of them equal? Yeah? Let's see if we can find it. Horrible. No, that's all kinetic. It's right here. Somewhere right in the middle, right? Somewhere right in the middle of the journey on the right, that is where kinetic and potential equal. Everybody okay with that? So what is happening on this object's journey is that there's always a conversion from kinetic to potential. You okay with that? Right? I'm not sure if you're seeing this here, right? The last bar. You see the last bar is green and blue. See that? The last bar is green and blue. But look at the height of that bar. Is it ever changing? Always the same. Right? That bar is called the total energy. Total energy always stays the same. In a virtual world. In a real world, what will happen? It will get smaller, right? It will get smaller. Why? Why? Would a pendulum move forever? No, because it loses energy. So what? Gravity, sort of, something else. Resistance of the air. Air resistance, we call that damping. Right? So because it loses energy, this total energy bar here will not remain the same. All right, nice. So I want you to see that simulation. No, I don't mind. I didn't mind. You say it now. Well, yes.
No, I can't. Just if I'm on walk with my.
All right. Bad news. The other Jonas. Pendulum. I know it's in your handle, but your mic never ever open up. Right? Jonas here is the same thing that we just explained about the pendulum.
Yeah, RT is the science. After student presentation.
Alright, so nice. So that gives us an idea of how to do these things, right? Let's take a look at how to solve some questions like this. Let's start here now. It's page 62. Page 62 on the topic by topic. Page 62 on the topic by topic. Right, go to page 62 and then we correct it all together, right? Somebody get pen back and do that, please. Page 62. So that. So I'll do here the topic so. That is. That. I'll get that summary and we'll do it. People, I don't well, put up question. I have question. Topic
So that's, we do we have it from the definitions. You say, yeah, everything. That's, I think, yeah, that's it. You know, I think we need to shut for that. We do that material.
That's kind of went to the other. Form the form go ahead. Form the form. Physics idea. That form what things. Yeah. So I think you can figure that we have to buy that first. Half like and these are. Well, that's on tomorrow, Friday. I mean, tomorrow, Saturday. Monday, Tuesday.
Tuesday from one, go on to five. See how.
Tuesday only. Well, Max and then. Max is one, right? half-life and energy. I had a good one. Finish, I have to. Finish. Is that? You're done? Well, you're gonna start. What's the name again? Okay, no name, let's go. No name, we have a pendulum, it swings from A to B to C and then back to T. A and C are the furthest points. What type of energy it has at A? Potential energy, very good, no name. Next one, no name. B. B is kinetic, okay, good job, no name. And C, no name. Potential again, very good. Right. Let's take a look at part 4. Another point D is situated midway between A and B. If the pendulum is returning to A to complete an oscillation, explain what type of energy is increasing and why. What type of energy is increasing and why? So let's go back to the diagram. Not Sanja. Sanja. No. Sanya. Sanya, help me with that now. So what type of energy is increasing? Look at where it is. It's at D. So it's going from B to E. What type of energy is increasing and why? Potential is increasing and why? What is the object losing? No, gaining height. But what is the object losing? What type of energy? Kinetic. So the object is losing kinetic. And from the conservation of energy, if you lose one, it's converted into something else. So you're losing kinetic, that is converted into potential. All right, write that down. So you're losing kinetic energy. which is converted into potential energy. Or you could say it's slowing down and height increasing. That could probably work as well. Right, that's A, B, C, that's part 1, 2, 3, 4. Part D, easy calculation, tell me what you got here now. Alright, book it out fast, wait, Nanya. Real easy. Oh, that was the about.
I'll give you this one.
So, let's start over with everyone.
Your result. My results.
Yeah. Ready? Elena? How much you got? 5. So E is equal to a half mv squared. So it's a half by 0.4 by 5 squared. So yes, that looks like 5 what? 5 joules. Easy, right? Let's go a little bit harder. Any questions online? Wait, online over there? Who online yet? Sanjay, any questions? Sharon? Ashish, are you there?
One.
Hey, good. Maybe bring up the words. Right, what's this one here? Let's see if we can find the velocity. This is on page 66. Page 66. You have to think it through, right? Think of what energy is being lost and what type of energy is being gained. Think about what is being lost and what is being gained. This one a little bit tricky, all right? Page 66. Don't worry with the first part. The first part is just to explain energy. I mean conservation of energy. What is? Oh, I'm so close. I can't. Start, yo.
Yes. Oh, she done wrong.
Who?
She done.
Sì, no, però vedo.
It's not.
Oh, but più che la razza dai. It just didn't that's not staying in my head. Let's just give trouble or you'll talk plenty or answer plenty. Like when I forget I just forget the name. Don't know what's going on now. Yes, no. But the name's so close and that giant. Huh? But which one was looking at that? Right? This one a little bit harder, will you? Right? What type of energy the ball has before it falls? Potential, right? Because he has the ball up here, 1.5 meters up here. And then when it releases the ball, what happening? It being converted into what? Kinetic, right? So think about it. How are we going to find the velocity? This one a little more challenging. Think of the energy it has before. I thought maybe I'll pinch a little while to show it. Right? Find what you could, right? Right, so here's the hint I'm willing to give you. Find the type of energy it has up here. That'll be what? And all of that is being converted into. So when you find the gravitational, make it equal to the kinetic, and then solve for B. Okay? Right, so while the ball is up here, it has all potential energy.
Oh,
And when it falls, just before it hits the ground, all of the potential is equal to kinetic. So you have to find kinetic after. So, please give that number. Well, figure. Right, let's see what you have. Potential energy is equal to your mass, which is 0.43 gravity 10. And your height is 1.5. How much is that?
wait, what? Oh, 6.5.
6.45 joules. Anybody have that? Yeah? So now the kinetic is equal to 6.45 joules. We have to convert kinetic into potential. I'm sorry. That potential is converted into kinetic. Now we have to use that to find velocity. So 6.45 is equal to half mv squared. Right? You're gonna make v the subject of the formula. Okay? Carry across 2. So that's 2 by 6.45 is equal to mass. The mass is 0.43 by velocity squared. Carry across 0.43 and then what? And then square root it, right? So you have to be able to do subject of the formula good, huh? And then you square root everything. That's right. Multiply by two and then divide it.
So, like 0.4.
Oh, yeah, yeah, yeah. A half by 0.43 and then divide. You can do that. Ah, which one?
Scroll.
It's your.
Scroll.
Yeah.
The answer.
Scroll.
Oh, velocity is 0.45.
No, it's 0.43.
Oh, shall I get it? Amelia, where? 28 when you work out that.
Being MG is more.
12, but yeah, it might be a bigger value. I think about my calculator. I know my calculator. Work it out then. Oh.
That's 5.
Just use the arrows.
Square root of 2 by 6.45 on 0.43. I got 5.47,
So 5.5.
5.5 or 5.48. Yeah, 5.48. Right, make sure you can make this out to get the formula, yeah? Copy it down. I want to show you a shorter formula that you can use. You want to do all of that. Copy it down though. So instead of doing all that, there's something else you can do, right? So you can add this to your formula list. If you want, you could do something like this. You could say, well, here's what. All of the potential that was converted into kinetic. We know kinetic is a half mv squared. We know potential is mgh. And what I can do from right here is make b the subject of the formula. M will cancel. Multiply by 2, you'll get b squared is 2gh. And then find the square root. So this little formula here, b is the square root of 2gh. You can use that to find anything you need. Right? b is equal to the square root of 2gh. Right? So write everything down in red. Eh? Not as the formula. Write everything down in red. Right? One more question. Go back to page go back to page 59 and we're done. Last question, page 59. Page 59, 59. Page 59, you're doing that whole question. You had to turn the page as well, right? Have two pages. Page 59. That's what-
จากประเทศไทยสู่อังกฤษปี
กลับมาแล้วภาพรามมันติดไปจาก
like in terms of you have the election, they must have was it's just the 4 2 3 out of BJ's so the match.
Yeah, that.
Then I give you. I give you 1 Newton.
Joule is 1 Newton meter.
Yes. Not done. Yes.
Yeah. Yeah. Wow. Good close. Are you gonna make it forward? I'm gonna wait.
Study.
No more. It's. I'll get three. Yeah. The kid with the body. That's so.
Pasawat sa money siya, no? Pasawat sa money ko.
With what? 121. 100 right? Yeah.
So, okay. I got you. Really good. From, okay, see, man.
No, that's.
Yes.
That's the last one, and we're done.
Yeah, probably not as so good, you know, see, man.
All right. In my next form of energy, besides mechanical,
Kinetic,
kinetic,
chemical.
chemical. Right, because mechanical and potential is made up in mechanical. So chemical example what? Gas. Okay. What's the next one? What's the next one? Anybody? Tasha. Which one? Oh, for chemical, yeah. All right. Okay, my next type of energy. Electrical. And you'll get them where? Power supply. You'll get them power supply or something like that, right? That could work. Right? Anything from the long table I give you. Say the SI unit of energy. SI unit of energy is what? SI unit is joules, right? Capital G. Define the SI unit. 1 joule is 1 Newton meter. That's all, right? Right, if you want a long definition, write this down. 1 joule is the energy. This one a little bit longer. 1 joule is the energy when 1 Newton moves an object 1 meter. 1 joule is the energy when 1 Newton, when a force of 1 Newton moves an object 1 meter. All right. Next, they gave us cement of total mass 60 kilograms. It's raised vertically up, so the height is 150 meters to the 12th floor of a building. Let's do what they after. Calculate the amount of energy that was needed to perform the activity. Energy is equal to mgh. So that's 60 by 10. 60 by 10 by the height. The height is 150. How much energy is that? What? 90,000 joules. If the activity takes 20 push-ups and then give you the power formula. Oh, sorry. So you want to look at the handout?
No.
This.
All right, so I'll give you the formula. Power is equal to energy divided by time. Right? Energy divided by time. The energy was 90,000 and the time was 25 seconds. Right? Power is energy on time. Write that down, please. 25 seconds. How much is that? 3,000. 3,600 watts, but they want the answer in what? So that would be what? 3.6 kilowatts, right? Divide by 1,000. Divide by 1,000 to get kilowatts. And lastly, friction. If friction was present, would the power be larger or smaller? Right? If they included friction, would the energy be larger or smaller? Larger. And if the energy is larger, then the power is larger.
Why?
Because power is energy divided by time. So if the energy bigger, you just divide by time. Alright? So if friction present, the power will be larger because the energy required would increase. Alright, nice. So that's the end of the first part of mechanics. At the end of mechanics, so what we have to look at next is hydrostatic pressure and a kinetic principle. Right? We'll do that first thing next week. Right? Yeah. We'll stop there. No more. No more. We'll stop there. Oh wait, well if you get close, man. Hello, what? Hello, close? What do I do?
Nobody gonna reach yet.
Ah? Let us see if we get close or not. That's not, I was just trying to find the one with everything. Hydrostatic, we're not doing that. Mechanics review. Right? It might have a question that it can't do, but I small thing, I'll give guess it. That's everything we did, plus, I think there's a question on pressure, but I might figure it out. Wait, everybody else. All the people online and log in.
So,
Huh?
You there? So yeah, KFC man, that's up right here.
Alright, let's start. I'm telling I just have one today, dude, right?
Let's see. Yeah.
Master blood board.
Forget it. It's fun.
Created by the government.
It's good, yeah.
Ah, they get kicked out so fast.
Oh, I'm sure that we don't think. Why did you with someone? Oh, I'm missing someone. No. No.
You catch back up here. It's a hard one.
Then.
Everybody get that one wrong?
Yes.
1 million top, a million, going on total. That's a. Easy, they got easy one here. We'll change. Sanjaya. That. Second, nice. Channel to the manager and doing so bad to do the one. But I'm in here going.
Get up.
Just show a little. Just show a little. Don't just get it formula.
Oh.
There goes security. KFC. That's Jaya, bed, Dana. Good job, Papa. Good. Let me see what I figure this out. Rate of doing good. Just give it. King of doing good. Keyword is rate, huh? Rate is time. Power. Because I got a chance to catch up to me here. 3 more, 4 more. Oh, you might know this one. You might have a guess. All you guys will guess it because it's hydrostatics. I'll give you a hint. Pressure is force over area. Pressure is force over area. That's the hint I'm giving you. So it's force. Let's make force subject. Alright, so we know the good guesses now. If you go lower into a liquid, what will increase? Think if you swim lower in a pool. Alright, this one hard. Either way, I don't want to guess. This one hard. I didn't show this subject. The answer is something called beginning with U. Neto. Something beginning with U. UP. Possible answer will be then. No KFC manager, no net one Starbucks. Objective float, what must happen? After the upward course on it.
Yeah.
Right, let me soon take it. I mean, yes, yeah. But I mean, we have to wait this place. It didn't specify which mass and weight. Right, good job. Yeah, who comes second and third?
Yeah.
So KFC wasn't top 5. Alright, online, that's it here. Right, physics people, enjoy your vacation. right? We start back the first Saturday when school reopen. No, now when school open, before school open. I think it's in third. Right, Dr. Log out. energy, right? Right, last part of radioactivity, I think the last thing is of binding energy. For nuclear. Alright, so the last thing that we have to do is the half-life. Alright, do I do the integration proof for it? Try to make it sound fun. I'll still show you. Alright.